Hello, I'm Channa Bankapur. I'm going to discuss my solution to the LeetCode problem 132 pattern. It's today's problem in the October LeetCoding challenge. So the problem definition is we have an array of n elements or n integers, and we need to find if there is something called 132 pattern. 132 pattern is a subsequence of three integers, right? These three are integers, nums of I, nums of j, and nums of k. There, among these three numbers, the first one, nums of I, is the smallest of the three, and nums of j is the largest of the three, and nums of k is somewhere in between these two, right? That's why they call it as 132, right? It's a decision problem. We need to find if there is at least one. All right. So a simple exhaustive approach or brute force approach would be try for all subsequences of length 3 and see if there is one, right? There are big of n cube number of them. And that's why we have a big of n cube solution, which works without taking extra space, right? But obviously it is too inefficient. There are actually big of n squared trivial solutions also. I'm going to skip them. They are already hinting that there are big of n log n and big of n solutions which are more efficient. So I'm going to go with these. So I'll start with this idea which is going to lead to big of n log n solution, and then I'll show how to improve that solution to get a linear time. All right. So the idea goes this way. We have this array of n elements which are normally indexed from 0 to n minus 1. And when we find the triplet, that subsequence of three elements, say the middle one is the ith element here, right? So the middle one is the highest element, and that has to be like something called three. Like we say that pattern of 1 3 2, right? One is somewhere in this range, three is at ith place, and two is somewhere here, right? So for a given I, how do I find something like this? So for whatever the value of nums of I, we want to find something lesser than that in the range of 0 to I minus 1. Whenever we are finding the lesser one, and in the range of I plus 1 to n minus 1, we want to find something in between those two, right? So ith value is kind of fixed. There is only one number in that range. But when you consider the 0 to I minus 1, we can find anything which is lesser than 3, right? There are many choices, but we can greedily choose the minimum in that range from 0 to I minus 1. So that gives us more space for choosing 2, right? So that's why we can always easily find min up to some ith place. So min up to always starts from the first element, and then it always keeps dropping, right? It's flat for some time and then again keeps dropping. It'll never go up because we always start from 0 and then go up to some I minus 1. All right. So that's how this can be found in linear time and linear space. So we have it readily available, right? So whenever I'm here, I can figure out the smallest from 0 to I minus 1, which is stored at this place. If that is not smaller than nums of I, obviously this triplet is not useful, right? So suppose it is useful, then what we need to do? We need to find a number in the range of I plus 1 to n minus 1, which is in between this min up to I minus 1 and nums of I. Nums of I being higher, min up to I minus 1 is lower. We need to find something in between, right? And one thing we can notice here, that's not going to be easy as constructing something like this. So so we can make one observation. We can remove few things which are going to be useless. What are those? The numbers which are even lesser than min up to I minus 1. Anything that is lesser than or equal to that are useless anyway, because they will be lesser than or equal to 1 in our case. So which are going to be not a candidates. And and if I just traverse from from end to back to or end to begin, so the min always keeps increasing in this order, right? So whatever we removed is not going to be useful in the future, right? So that's why, let's see, if I use a method where I go from end to begin, and I have already constructed this min up to array, so that is readily available, and I could start from n minus 2, because n cannot be I, or n minus 1 cannot be I, so ith one is going to be n minus 2. All right. So with that, what we can do is we can have some kind of priority queue at the right side, where it's based on the essentially min heap, and anything which is lesser than the min up to this I minus 1, we can remove them because they'll never be useful, right? And then see the minimum among them, because which is anyway going to be greater than min up to, right? So that is obviously a good candidate. If that is lesser than nums of I, we have a solution. If we don't have a solution, we can again move I and then figure out if there is anything more. So what the good thing about this one is, any numbers, any of those numbers which are lesser are not going to participate in the future, future comparisons, because they were smaller and then we already removed them. And anything which is, which was, suppose we had a min here at this level, and so there were some numbers at this level which were there in my heap, but they were candidates. But when min actually increased, those are not the candidates anymore. I'm going to remove them. So they are not going to be compared later, right? So this is the simple approach I'm trying to use here. So let's see whether this approach can lead to a proper code. Let me show you in the code. That should be easy to demonstrate. So what I have here is, I have n elements in the array, and in this block, line number 6 to 10, I'm constructing that min up to array, which is going to be which can be done in linear time and then linear space. All right. So now I'm going to have this set. Set is essentially for me min heap in this case. So instead of using priority queue, I'm just using set. That it has the same big O complexity. So what I'm going to do is, I'll insert the last element into the set to start with, and then I'm starting from I equal to n minus 2 and all the way down to 1, right? Because I cannot be 0 or n minus 1. It has to be somewhere in between, right? So these are the ranges, range of possible values for I, and obviously I keeps reducing it. So as I told you, in my set or in my min heap, whichever is lesser than, so this is the smallest element. If that is lesser than min up to I minus 1, it's going to be useless anyway in the even now and any time in the future. So I'm going to erase all of those things, right? So this is one time you're erasing them, and this is the situation where we can actually figure out there is a solution. So now, if the smallest of the elements from that I plus 1 to k, which is greater than the min up to I minus 1, if that is lesser than num psi, we have basically a triplet, which is that 132 pattern. I'm going to return true, right? So if not, what I'm going to do is, I'll just have to go to next I, but before that I'm going to push this ith value into that heap, min heap. I could have checked whether this is good enough to insert here, but I'm not going to worry right now, because anyway when I reduces and min up to I minus 1 could be something higher, so I don't want to do it now itself, right? We can always do it in this while loop, right? So that's why this works. And let's see whether the code works, right? Obviously, if you don't find any, you're going to return false, right? So yeah, it's working for the sample test case, and if I submit, it's going to be accepted, right? So let's look at what is the time efficiency of this. So we are using a set here. Set essentially means it's a balanced BST. So all the operations of insert, delete, or even access, all of them are going to be big O of login operations, right? So other than those big of login operations, if you look at how many times or what is the complexity of, so essentially how many times uh, this operation can be performed, or any other operations, you can look for even insert also. So how many times? This is clearly insert can be done only linear number of times, because it is not within this while loop. But erasing from that min heap is basically something inside another while loop, so looks like it is more expensive. But if you observe, every element is inserted into the min heap once and then erased out of that in once. So obviously the number of times you perform this operation is not going to be more than the number of times you do that overall. So that's why this is also linear in terms of overall number of times it executes. Just that the cost of these two are big of log n. By the way, cost of finding the min element in BST, normally it is big of log n, but in this case, begin value is already stored in constant time. So the begin value can always be obtained in constant time. The set always maintains that kind of information. So this is going to be constant, right? So that just that erase and insert are going to be big of login. And because of that, the whole thing works in big of n login time, right? So we use some kind of priority queue or min heap on the right side. On the left side, it was simple, finding the min up to some point, right? So how do we make it, better than n log n, like linear time? So one thing we can change is here, instead of using, a min heap, where we are getting rid of all the elements which are lesser than, min up to I minus one. What if we only get rid of the ones which are kind of needed right now, right? We don't have to search for everything and then remove it, right? If you don't put that much of pressure, this can be improved further, right? So what I'm going to do is I'll quickly show a way of doing that, and then maybe let's get to the explanation. So instead of using set, what if I use a stack here, right? This is actually a more popular solution, but I'm just building the motivation to that. If I use a stack of these potential elements on the right side, so obviously stack uses push. So I'm going to use push here, and stack uses is empty. So I need to make sure it's whether it's not empty, right? So not empty. And so it's just about a Boolean thing. It's whether it's empty or not. And instead of, because it's a stack, you can get the top directly. So I'm going to get the top here, right? So that's all I need to do. And yeah, I need to push it into this stack. So I'm going to use push here, right? So push, but sorry, this is pop, right? So I'm going to pop out of this, right? Pop doesn't need any parameters here. And the same thing again, whether the stack is empty. So if stack is empty, obviously you don't want to do it. So if stack is not empty, and we want to take the top again, so top of this one, if this is less than the element, we can return true. Again, I need to push here, so I'm going to use push operation, right? So that's all. As in, it's not a very uh, lot of changes. The idea is still same. So why this is good enough here is, see, whenever we are trying to see whether there is an element which is smaller than the ith element and greater than min up to I minus one, you have to find just one. It's not like you have to find the smallest which is greater than the min up to I minus one, right? So that's how stack is good enough to say that. So it's going to still remove all the ones which are at the top and that are not good candidates. You remove that. But if they are somewhere hidden down, down there, if they're towards the end, they were not a threat at the beginning, but then again they became lesser. So those are the things I could remove them, but I'm not really, worried so much about removing them, right? So that's why they could remain for a longer time, and we are okay with that, right? So and because of that, we can find some number which is at least, in that range, right? Sometime it could be much nearer to ith element than somewhere further, right? Because if you find in min heap, when I find the smallest, it could be far away, right? So this is still good enough in terms of, solving this problem, right? And that's why this works. And yeah, look at this, it accepted. And now if you see the time complexity of this, these things, right? Finding top or popping or pushing, all of these are constant time operations in stack, right? That's why the whole complexity, is brought down to just linear time, right? So, but I think for understanding, min heap is better. But yeah, for efficiency, stack is better. All right. So let me know if this understanding is proper, or if you have any different way of explaining or a better solution, more intuitive one, let me know in the comments. Otherwise, subscribe to the channel and, like the video. All right. Happy coding.